Welcome class to this lesson on electronic transmission controls. This section that we're in now is automatic transmission electronics and transmission diagnosis. We went over a little bit of electronic transmission controls when we were talking about valve bodies. We're going to dig a little deeper into that now. Basic objectives of the class is we're going to explain how these automatic transmissions and transaxles are controlled electronically. We're going to explain the different function of the sensors and switches. We're going to talk a little bit more about the types of transmission solenoids. And then we're going to get into adaptive strategies, and that's how these transmissions adapt to wear or different conditions that they're faced with. All right, as we started this lesson, as we know from our history lesson on automatic transmissions, we've had electronically controlled transmissions around since the 1990s, early 1990s. By the late 1990s, almost, if not all, transmissions were electronically controlled. We're using shift solenoids and stuff and pressure control solenoids to more accurately control pressure and more accurately control shifts. To do this, we're using a PCM or TCM to operate and control the shifting functions of the transmission. PCM, if you remember, is a powertrain control module. TCM stands for transmission control module. In the early days of electronic transmissions, it was relatively common to see a separate transmission control module and for the transmission and a PCM or an ECM for the engine. Then they kind of went to where the PCM, many manufacturers are using just a PCM for powertrain control module to operate the engine and transmission. But as these systems have gotten more sophisticated, and as we now have our CAN bus, if you remember from Engine Performance 2, and we can communicate much better between the modules, and we can use less wiring to do it with, you're starting to see more and more vehicles with a separate transmission control module. The other thing about that on transmission control modules, you know, many of our PCM and TCMs are going to be mounted under the hood, separate in our aluminum cases, usually finned to help cool them. We're starting to see more and more transmission control modules mounted inside the transmission on the valve body with the solenoids. So if you needed to replace solenoids, on some of these, you replace the whole assembly, module and solenoids all together. That's also another reason as we replace transmissions, a lot of your newer transmissions need to have that module reprogrammed or reflashed. Even transmission control modules that are separate, you're seeing more and more of those that need reflashed before we go and drive that new transmission. Electronic transmission transaxles still use hydraulic pressure to operate the transmission. That hasn't changed. Still have a fluid pump. We're still pressurizing fluid using a regulator to control that fluid pressure. But now we're using solenoids to help do that much more accurately. We're using a pressure control solenoid to help control that pressure control valve. We're using shift solenoids to control that fluid pressure and direct it to get our certain transmission shifts. So they're still using hydraulic pressure, but now our solenoids are controlling, we're using solenoids to control that pressure. We can do it much more accurately with solenoids than we could when we just have a throttle valve and a governor controlling our pressures. Because remember, the transmissions, even electronic ones, need to know how fast the vehicle is going. You need to know what kind of load it's under. But now we're using electronics to tell the transmission exactly that information. And just like from there, we're using inputs and outputs to control, using inputs to control outputs to control these shift points. The process that happens in a transmission control module is the same process that happens in a powertrain control module with our engine. If we remember from our engine performance 2, we have inputs coming in. We have storage on the computer that has information stored. Certain parameters, certain criteria that the module looks at to determine how to control the transmission. So inputs come in, those are compared with the storage information on the PCM. That information is processed, and then we control our outputs. So inputs, storage, processing, outputs. The same functions that happen with our engine computers are happening with our transmission computers. Inputs on our transmission for our transmission control module. First, we have our engine inputs. Something, and I'll bring this back up when we are talking about diagnosis. Always diagnose your engine first. If we have engine performance issues, if we have codes related to sensors on our engine, that can affect shifting in our transmission. There are many times when transmissions are condemned or attempted to be repaired when the problem was in the engine, not the transmission. Customers complaining about how it's shifting. A shop puts a transmission in it, thinking the transmission's no good, and it still shifts the same way because our problem was engine performance issues. Always diagnose those first before we get into our transmission. Even if we have a transmission burn up, clutches have all burn up for some reason, if we have engine codes or engine performance problems, let's solve those before we put the new transmission in, because we could end up ruining a brand new transmission if we're having problems with our engine controls or the performance of our engine. Transmission inputs. Before I go much further on transmission's inputs, and I'll say this again when we get into the diagnostics of it, before we make any diagnostics on the transmission, we need to be checking what's going on with the engine. Malfunctioning engine sensors or malfunctioning engine performance can cause shifting problems in the transmission. Always eliminate engine problems first before we deal with the transmission. Because even if the transmission is burned up, it's slipping real bad, clutches are burned up, if we have engine codes, we want to diagnose those because that could have led to an improper shifting transmission, which could lead to a damaged malfunction transmission. So we wouldn't want to put a brand new transmission on an engine that is malfunctioning, because we could end up burning that one up also. So we've looked at our transmission, our engine inputs. We won't go into great detail on those because our engine performance class, we should have a pretty good idea of how those sensors function and how they operate. The transmission uses those to get an overall understanding of the load that the engine is under. Our transmission inputs, we got what we call a transmission range switch, a transmission fluid temperature sensor, pressure sensors or switches, and then speed sensors. And we'll go into each of these in a little more in depth. And then our other inputs are our brake switch. These are our primary inputs into our transmission control module or our PCM. Here's kind of a picture of where some of these sensors are. On the side of the transmission on this one, we have an input sensor and an output speed sensor. We're going to have some sort of connector that goes through the case of the transmission, because we have solenoids on the inside of this transmission, and we need to run wiring from the TCM or PCM into those solenoids. So we're going to have a connector that goes through the case somewhere on the transmission. That connector is going to have an O-ring out around it, obviously, so we don't leak fluid out of the transmission. And then our transmission range sensor, vast majority of those are bolted to the transmission around the manual shift valve, or the shift lever for the manual valve. In other words, it monitors where you put the gear selector switch. All right, starting with our different inputs. Our transmission range sensor. This tells the PCM what drive range has been selected by the driver. Did I put it in reverse, neutral, my top gear, overdrive? Did I put it all the way into low gear, manual low gear? Okay. That is what the transmission range sensor is telling the vehicle. What it does is, if I put it in low gear, then it'll limit the upshift of that transmission, because we're telling the transmission, I want to be in low gear. Now, in many electronic transmissions, if you rev it up high enough, there's a programmed into the control module, programmed into the transmission, it will go ahead and shift to save the damage of over revving the engine. But for most cases, in most situations, the transmission range sensor tells the vehicle what gear the driver wants it in. So if you put it in a low gear, it's going to limit the upshift of that transmission. It's going to replace the neutral safety switch and the backup light switch. In other words, a neutral safety switch doesn't allow you to start the vehicle unless it's in park or neutral. That way, if you put it in reverse, if you had it in reverse or drive and started it up, the vehicle's going to try and take off and move before you're ready. So that is what the purpose of a neutral safety switch is. You can only start that engine whether it's in park or neutral. On non-electronic transmissions, this was always a separate switch. Now we can incorporate that into our range select switch, our range sensor. It also has circuitry in there for our backup light switch. or our reverse light switch. In non-electronic transmissions, there was a separate switch that when you put it in reverse, it closed the circuit to turn your backup lights on. So people knew you were backing up. Okay. Now, on the vast majority of transmission range sensors, that's built into the sensor. These can also be called manual lever position sensors because it is monitoring the manual position of the shifter. Something very important on these, intermittent issues in these or codes in these can cause shifting problems. Ford had a lot of trouble there for a while, that intermittent glitches in these sensors would cause the transmission to have trouble determining where to start at, how to shift the transmission, and you would get erratic shifting in these transmissions. So it is possible to have one of these out of range or have glitches in these that cause transmission shift problems. The vast majority of these are just an analog resistance type sensor. You put it in gear, it sees that going through a certain resistance, it tells the computer, I'm in first gear, I'm in second gear, I'm in third gear. Or they'll have separate wires for each one, and once the switch closes, it knows, oh, I'm in this gear. Okay. You can check these with ohm meters. You can check these with your scanner to see if you're in the gear that you're supposed to be. The next input is our transmission fluid temperature sensor. These are thermistors, just like our coolant temperature sensors. They're negative temperature coefficient. In other words, as temperature rises, resistance decreases. So you can actually check these with an ohm meter if you needed to, but for the most part you're going to use your scanner. They can also be called oil temperature sensors. They're used to help determine the best shift points and regulate line pressure. When the vehicle is cooler, line pressure is going to be higher because seals, when they're cold, don't seal as well. So they're going to increase the line pressures, make sure those clutch packs engage properly. Also going to maybe alter their shift timing when it shifts when it's colder. Maybe shift it a little later to where so the vehicle can warm up a little faster. They also use it in the control of the torque converter solenoid. If the temperature gets too hot, first of all, on many transmissions, the transmission temperature has to be a certain temperature before it'll even engage the torque converter clutch solenoid. Okay? The idea is if the transmission torque converter is slipping a little bit, it'll get up to temperature faster. Once it gets up to that temperature, then at cruising speed, we can engage that torque converter clutch solenoid. If the transmission gets too hot, many times they'll disengage an overdrive. Okay? Because in overdrive, it puts greater load on that engine, on the transmission, with a greater risk of it slipping and creating heat. So they will disengage overdrive on many transmissions if the temperature gets too high. So this is, I would say this is just as important to the transmission as the coolant temperature sensor is to the engine. Okay, this would be a higher priority to the transmission controller than the engine coolant temperature would be to the transmission controller. If you remember, one of our inputs that we use from the engine for the transmission is the engine coolant temperature sensor, but the transmission coolant temperature sensor or the transmission fluid temperature sensor is more important to the transmission. Most of these are located on the valve body. A lot of times they're part of the pressure switch assembly, which we'll talk about here in a little bit. Sometimes they are a switch screwed into the side of the transmission. The line pressure runs on the back side of it, and it can determine the temperature of the transmission. Aftermarket setups, you can screw in an aftermarket temperature sender like in a line pressure port and put a separate gauge on if you're getting into towing of a vehicle and you don't have a temperature gauge for your transmission. A lot of times it's good to put a transmission temperature sensor and a gauge on so you can monitor it. But the factory transmission sensor is used for shift points and also to help control line pressure and the torque converter clutch solenoid. This picture is a picture of our pretty common range sensor. This one's I believe on a 4L60E. That's a 4-speed GM transmission, but these are used in different shapes, different configurations on basically every electronic transmission out there. The control module needs to know what gear is selected on the transmission. Here's kind of another example of that. If you have a vehicle to where you got this park reverse neutral drive, and then you can go into manual mode to where then you can manually shift and downshift the transmission. That is also part of many times your manual lever position sensor or your transmission range sensor. Here they're using the resistors. Depending on what shift you're wanting within your manual position, will tell the computer how to upshift the transmission. Okay. The manual lever valve, if you remember from a hydraulic, stays in the drive position, and then they use solenoids to upshift or downshift the transmission. Here's a picture of our temperature sensor. This is just, if you want to get into checking these, again, a lot of times you got a scanner on it. You can read the temperature of the transmission. If for some reason it's giving you a number, like it's been sitting in a garage all day and the garage is 70 degrees, but you hook your scanner up and it says it's negative 20 degrees, then you most likely have a bad temperature sensor. You can ohm it. You can check the resistance across. Here's kind of a universal chart, but as I've always said, always check your service information to see what the specifications are. Sometimes the only way to replace a temperature sensor is part of an assembly, like a solenoid or a pressure switch assembly. But if you can replace a sensor separate and it's malfunctioning, causing shift problems, maybe pressure problems, then we can diagnose that and replace the sensor separate. Pressure sensors or switches. A pressure sensor is a transducer, okay, which is a variable resistance that produces a signal that is relative to pressure. In other words, as pressure increases, resistance is going to change. As pressure decreases, resistance is going to change. Not necessarily in that order. In other words, these pressure sensors can be either way. When pressure increases, resistance may increase or resistance may decrease. But it should work the opposite way once pressure decreases. That would be a pressure sensor. A good example of that is a line pressure sensor that you find on many of your newer electronic transmissions. So the vehicle can actually monitor what the actual line pressure is. You also have pressure switches. These are on-off switches. When pressure gets into that circuit, the switch closes and tells the PCM or TCM that there's fluid pressure in that circuit. It can't tell you how much fluid pressure, but it can tell you if there's that pressure in that circuit. Usually has to be a certain amount of pressure to trigger that switch. They use these to help in TCC lockup, shift timing, and it also helps in transmission diagnostics. They're monitoring that pressure, and we'll talk about this when we get into adaptives. The transmission monitors from when they command a shift and when the shift happens. That time span of computer commanded the shift to happen at this point, and it took this amount of time before the shift actually happens. If that gets too far apart, it'll set a code. Or they use that in their adaptive strategy to learn how to adjust for wear, to adjust that shift timing. Okay, so these pressure switches are very important on a transmission. Here's an example of these pressure switches. This is one on a 4L60E. As you can tell, this transmission's got some age to it. Those are kind of dirty, but that's pretty common in the transmissions with some age. And you see the holes to the clutch circuit. In other words, it can tell when it's in first gear because pressure runs through the valve body to the clutch, and that hole or circuit goes up to the corresponding switch in the pressure switch assembly. And in this switch assembly, it has the temperature sensor in this particular switch assembly. It's near the front there, but you can't really see it because it's so dirty. And that could cause a malfunctioning temperature sensor reading also when they get this dirty. But they have O-rings that seal it around the circuit. If those O-rings are bad, then it won't seal. You'll actually get leak in that circuit. So that could set codes, and it could cause a transmission to shift poorly. That's why when we rebuild transmissions, many times it's recommended to replace that switch assembly. At the very least, you clean it up and replace the O-rings in it. So make sure it seals properly to the valve body. Here's kind of how they work. These switches can be normally open or normally closed, and then when pressure acts upon them, then they operate in a different way. Okay, so the computer's monitoring it. If it's supposed to be normally closed, and then when it gets pressure, it opens up, the computer will know that, and then control the transmission accordingly. But this is kind of how they work. They're applying pressure, moving a contact in a switch. Okay. Speed sensors. These are sensors in the transmission that monitor different parts of speed of the transmission, and we'll talk about each one of those here in a minute. These can be magnetic or Hall effect sensors. just like our crankshaft cam position sensors. Okay, if they're magnetic, they're going to generate a voltage, generate an AC voltage, if you remember. Then if it does that, then that gets converted to a DC voltage, usually in the computer. Where our Hall effect sensors actually produce our square waveform, almost like an on-off frequency signal. They can be either or, so you want to make sure if you go to test these that you know what kind of sensor they are, and we should be able to find that in our diagnostic information. The two main sensors are our input speed sensor and our output speed sensor. The input speed sensor is also called the turbine speed sensor. This is the input shaft of the transmission. If you remember, the input shaft is connected to the turbine impeller of the torque converter. That's the one that's not hooked to the transmission, the converter housing, that when fluid coupling happens, it spins this turbine impeller, which spins the input shaft of the transmission. That is what the input speed sensor or turbine speed sensor monitors. How fast is the input shaft turning? Not all electronic transmissions have this. Your earlier transmissions, like your 4L60E that we've seen several times, does not have an input speed sensor. They're monitoring engine RPM as basically their input speed sensor, along with some logic from the output speed sensor to determine the actual speed of the turbine. Okay. Our output speed sensor, also called the vehicle speed sensor, monitors the output shaft of the transmission. This is the speed of the transmission. This takes the place of our governor. This is why we don't need governors on electronic shifted transmissions. We have a sensor telling us how fast this transmission is turning. Okay? So we can use this to determine how fast, and we can use our sensors on our engine to tell us the load. With our throttle position sensor probably being the most prominent sensor that they use to determine the load of the vehicle. Okay, that kind of takes place of our throttle valve on just our hydraulically shifted transmissions. There are many uses for these sensors. Okay, a vehicle speed sensor, they use that not only for the control module to know how fast the vehicle's going. It feeds the information to your PCM or TCM, which communicates with your instrument cluster to tell you how fast the vehicle is going. It runs the speedometer. It helps in determining when the lockup torque converter engages, when the transmission shifts. All these are part of the output speed sensor. Another thing it does is if we don't have an input speed sensor, they need to know on overdrive transmissions with lockup torque converters how much slip is in that torque converter. If you remember that from torque converters. If that slip is too much, it will set codes. If that transmission is supposed to be, if that torque converter is supposed to be locked up to where there's no slippage or very, very little, and they monitor a lot of slippage, they're going to turn a light on because you could ruin your transmission, or definitely a sign of a bad torque converter. So what they do is they monitor their output speed of the transmission. They've already factored in gear ratios, determining on what gear you're supposed to be in, and then they monitor engine RPM if they don't have an input speed sensor. If that engine RPM is one speed and the output speed sensor is another speed, then they can use logic to determine how much slip is in that transmission, in that torque converter, and determine whether it's slipping or not, and then set codes accordingly. If it has an input speed sensor and an output speed sensor, then what they'll do is, to determine whether the torque converter is slipping or not, is they monitor the input speed sensor and the engine RPM, and then they can get an exact amount of slippage. Because if you remember, the engine is connected directly to the housing of the torque converter. So that's going to tell you what the one impeller or the converter pump speed is, the engine RPM will be. And then the input speed sensor will tell you the speed of the turbine or the input shaft. And the difference in those two speeds will tell you whether the torque converter is slipping or not. And it helps in the control of that lockup, and it helps sets code. A lot of your newer transmission will actually tell you, or most electronic transmissions will actually tell you the gear ratio. Using an input speed sensor and an output speed sensor, we can tell what the actual gear ratio of the transmission is in. If we're in first gear, we're running in first gear, it should be able to tell you what that gear ratio is. If that ratio is off, then they can set codes. They monitor that gear ratio because in first gear they're expecting a certain gear ratio. If the input speed sensor is turning at a much greater rate, a much different rate than our output speed sensor than what it's supposed to, it's going to show a gear ratio that is off, and it'll set a code. That's a good sign that the transmission is slipping. The clutch packs are slipping in the transmission. So as you can see, these input and output speed sensors are very important to electronic transmission. Erratic signals from these, no signals from these, can cause transmission problems. Okay? Very important that we monitor these and check these. Most of the time you can check them with the scanner, but there are some times when you have to get your lab scope out and actually check the waveform on these speed sensors, just like you would check them on a crankshaft position sensor. Our last input is our brake switch. Remember from our acronyms, the BOO, brake on and off switch. For a transmission, the primary use of this is to control the lockup of the TCC. Okay. On many transmissions, if you're cruising down the road and you tap that brake switch, then if your torque converter is locked up, it'll disengage that torque converter because it's thinking you're slowing down. Remember, we don't want to come to a complete stop with the torque converter completely locked up, because it'll act just like a manual clutch and it'll cause the engine to stall. Most transmissions with lockup torque converters have to be hydraulically in a higher gear than first gear for it to actually even work. So in many transmissions, even if the lockup was stuck, you could come to a stop and it wouldn't stall the vehicle because the hydraulic pressure that applies the lockup is taken away by the time you get down to first gear. There were some older transmissions. GM had one called a 125C. That was a transaxle, a 3-speed transaxle that had a bad problem with their torque converter solenoid sticking, and you'd come to a stop and it'd kill the vehicle. it'd make that solenoid open up, and you could start it up, and most of the times it would be free and you could drive it. But once you got up to speed, it re-energized that solenoid, it would stick again, and you'd come to a stop, and it would kill the vehicle. Okay, so that's a big reason why we have a brake on-off switch. But in case that malfunctions, most transmissions hydraulically cannot lock up the torque converter in first gear. That way that's just another safety feature from keeping it from stalling if that torque converter stays engaged when we come to a stop. Here's just a picture of that, just kind of a generic brake switch. It's located up by the actual brake pedal. It's a mechanical switch. When you push down on the pedal, that either opens or closes a circuit to tell the computer that the brake pedal is pressed. Now that we're done talking about inputs, let's talk a little bit about our outputs. We've already talked about some of these, or most of these, in our when we're going through valve bodies in our hydraulic sections. Okay, we have our shift solenoids. These are usually on and off solenoids, but even as we get in many of our newer transmissions, even our shift solenoids are going to pulse width modulated because they can better fine-tune the shift pressure and timing with pulse width modulated solenoids. But many of them, most of them, up to till we started getting into our 7, 8, 9, 10 speeds, and maybe even before that, most of them were on-off solenoids, or for our shift solenoids. A torque converter clutch solenoid, we talked a little bit about this. This can be an on-off solenoid or a pulse width modulated solenoid. Almost all our new ones are pulse width modulated, so we can control how that torque converter clutch engages. We don't want to engage it too stiff. There are some combinations on some systems where you have a combination of an on-off solenoid and a pulse width modulated solenoid. The on-off solenoid would engage to allow hydraulic pressure to the pulse width solenoid, and then the pulse width solenoid would actually be used to then control the torque converter clutch solenoid. The one I'm thinking of is the 4L60E. In those early days when they went from an on-off solenoid to a pulse width solenoid, in the first ones they just added that pulse width solenoid and kept the on-off solenoid as, I would think, a cost saving issue. They didn't have to redesign a valve body if they did that. They later redesigned the valve body and the transmission a little bit, so then all they had was just the pulse width modulated solenoid. But there are some cases where you have both. And we talked about this pressure control solenoid also is a pulse width modulated solenoid. They use that to determine exactly how much pressure they want the line pressure to be at. If they want that line pressure higher, like if you remember when we put it in reverse or manual low, we want higher line pressure because we think we're going to put the vehicle under a heavier load than if we are just in drive. Heavy throttle, we want higher pressure so we can engage those clutch packs tighter so we can shift a little later. Light throttle, we have less pressure, so quicker shifts, softer shifts. That's all controlled, the pressure is controlled by the pressure control solenoid. All right, We've talked about shift solenoids in our hydraulic section of our course. We'll kind of go over through them again or review. Here's a picture. Just as remember, we can have a normally closed or normally open solenoid. Normally closed means the hydraulic circuit is closed off, not allowing fluid through until we apply current, which energizes the electromagnetic coil, creates a magnetic field, pulls our plunger against the spring, and opens up the hydraulic circuit so fluid can flow through the solenoid. As you can see, the top one is off. When it's in the off condition, the line pressure is not able to go through the solenoid and apply through the control side. But as soon as we energize it, it turns on and line pressure is able to go through the solenoid. Here is a normally open solenoid. Fluid is able to, line pressure is able to go through the solenoid in its normal state. And then when the computer energizes it, it closes the circuit off. So fluid is, line pressure is not allowed to go through the solenoid. Again, we've went through these in our hydraulic systems, but this is just a review, and these are a couple good pictures to kind of get an understanding of the difference between a normally open and normally closed on-off solenoid. Here's another picture of our electronic pressure control solenoid, where we are using a solenoid with a valve to control the pressure in the transmission. So they're controlling the pressure against that spring and valve, and that valve then controls the actual pressure coming from the pump, actual line pressure of the transmission. Here's kind of a duty cycle, hydraulic pressure. As duty cycle changes, hydraulic pressure changes. Okay? Usually, as duty cycle increases, pressure decreases. Okay? As the duty cycle decreases, line pressure increases. This is how it is on vast majority, if not all, pressure control solenoids. All right, now that we've done talking about inputs and outputs of a transmission, we're going to talk about how this all goes together, how it all works. Okay, the PCM or TCM uses information from the different engine and transmission sensors and then commands the shift solenoids to operate, which controls not only controls shift timing, but it also controls pressure. This is that process I'm talking about. They're monitoring the engine load with the sensors from the engine. They monitor vehicle speed with our output speed sensor or our vehicle speed sensor. Then they're comparing those to determine when to shift the transmission. If you remember in our hydraulic transmission, governor pressure had to overcome throttle pressure as we're upshifting. When we went to downshift, throttle pressure had to overcome governor pressure so we could downshift, say we wanted to pass somebody. So in a hydraulic transmission, we had throttle pressure and governor pressure to determine when it shifted. In an electronic transmission, we are using sensors and switches to determine when that transmission shifts. Okay? The hydraulic pressure, again, transmission still works off hydraulic pressure. We're using the shift valve solenoids to control that and direct that hydraulic pressure to then act on our shift valves to shift the transmission or operate our torque converter clutch. Okay? and we're also using it to control our line pressure to either increase or decrease it. We're using this all together. Inputs into the transmission, there's data stored on it, they process that storage with the inputs, and then they control their outputs. And those outputs are the pressure in the transmission and our shift points and our lockup torque converter. Here's just kind of a picture of how they're doing this. As you can see, here's our transmission control module. We have the inputs coming in. Our ECM or PCM is communicating with our transmission control modules. It's telling them we're under heavy load, we're gradually accelerating, or whatever. And then it's controlling our solenoids to determine how it controls that fluid pressure, so we can determine when it moves those valves and when the transmission shifts. Remember, those shift valves are connected to the different clutch packs and bands. We're moving those shift valves to control the hydraulic pressure to our clutches or bands that then hold different members or drive or hold different members of our planetary gear sets to get our different gear ratios, to get our different shifts in our transmission. Here they're kind of putting it all together. As you can see, we have a pressure oil pump, our pressure regulator, which is controlled by our, here they're calling a line pressure solenoid. We call it our EPC, our electronic pressure control solenoid. We have our shift solenoids, our torque converter solenoids. We have our TCC control valve and our pressure regulator. All this, our hydraulics, are working in conjunction with our electronics to move our shift valves, to apply our different clutches and bands. Okay? And that's how we get our shifts in our transmission. All off our inputs from our different transmission and engine sensors. Now we're to our adaptive strategies. Okay, the main idea of an adaptive control or adaptive learning is to give the PCM or TCM the ability to adjust for wear in the transmission by monitoring that shift timing that we talked about. In other words, when the TCM or PCM commands the vehicle to shift, and when it shifts, they monitor that time frame, and then if it gets too high, then they adjust it by changing. Maybe they start shifting that shift valve sooner. Maybe they increase the pressure so it shifts quicker. They do that to adjust for wear in the transmission. Wear in clutch packs or bands, which would mean they would take longer for that clutch pack to apply. Wear in a pump, to where it takes more to build that pressure up. All right. All these could be wear that the transmission has to account for to adjust that shift timing or pressure, so we can get it back to where it was programmed to be. If a computer can't get it to can't get to that shift timing to adjust within a parameter, that's when it sets codes. Okay. Some two popular ways of doing this is Chrysler calls it their clutch volume index. GM calls it their transmission adapt pressure. Chrysler clutch volume index, the idea is that they're monitoring that shift time and they determine it's taking more volume of fluid to fill that clutch pack and apply that clutch pack. So it's That's why it's taking longer, and then they put a number to that, 80, 50, and there's specs on that number. You can look those specs up. A lot of times they are on that scanner. If those get out of spec, you get transmission shifting problems. As a matter of fact, this is one of these things, these adaptives, when we replace transmissions, we relearn those adaptives. We reflash the computer. A lot of your early Chryslers electronic automatic transmissions, you would repair or replace the computer, and there was a process using the scanner and actually shifting the transmission to reset these clutch volume indexes. If you didn't, the transmission was shifted improperly, and even a brand new transmission, if you didn't reset those clutch volume indexes, you could burn up or ruin a brand new transmission. Okay? GM calls it the transmission adapt pressure. In other words, they're monitoring that time, and then they usually increase the pressure to make that time shorten. If we increase the pressure that fills that clutch pack faster or applies that band faster, so then we can shorten the shift time. We can actually go in and see this on scanners. Our clutch volume index and our transmission adapt pressure. Other manufacturers are using the same strategy. They're just calling it different names and putting different numbers to it. Here's a picture of a GM on a scanner. If you're looking at their transmission adapts, you can see the different pressure changes, and they're putting a number to it in correlation to the throttle position. In other words, they're expecting, and this is the data that's stored on the computer that the TCM or PCM has to look at in conjunction with inputs to determine how to process that information and control outputs. Because it's programmed in the computer that at this engine load or throttle position angle and this speed, it should take approximately X amount of time to shift. So at 10% throttle, which is a light throttle, it's going to take maybe a little longer to shift, or it'll because they want the shift to be smoother. Then at a higher throttle, they may want that shift to be a little quicker, so we don't slip the clutches as much. If that starts getting out of those parameters, then they'll control fluid pressure to get those shift points back into the parameter, the timing of those shift points. And this is what it would look like on a scanner, to where we're looking at the PSI of different throttle position angles of what they're doing with the PSI. So at 31% TP, they're adjusting the throttle pressure, it looks like, down a little bit. With 31% TP2, they're adjusting it up a little bit, the pressure. That is all to keep the shift timing, shift points within range. Another adaptive they do, before I start talking about our default, is they have the ability to adjust how the transmission shifts depending on the conditions. I talked about this a little bit in Engine Performance 2, to where a teenager gets into a car, his grandma's car, and that teenager drives it much harder than the grandma does. The computer can adapt and learn to that logic. That is not stored heavily in the computer. They adjust a little bit to how the vehicle is driven or where it's driven. If you're driving up in the mountains, it's going to be under load a lot more often than if you're driving it in western Kansas, which is flat. Okay, so the transmission can adapt a bit to the conditions of the driver, or to the type of person driving, or how the person drives, and the condition they're driving in. That's another adaptive that's part of the computer. Now we're going to talk about our default mode. Your electronics transmission, when a fault is initiated, most codes set in a transmission, or maybe even some codes out of an engine, will cause the transmission to default to a certain gear. This is usually where the PCM or TCM has decided that this could cause damage to the transmission. So they lock it into a certain default gear. This gear is usually second, third, or fourth, depending on the transmission and manufacturer, depending on the application. Many of your early 4-speeds, it was second gear. As we've added more speeds, we change what gear ratio they've locked it in. Okay, so if you get a transmission, the customer says, this transmission, my vehicle, it starts out really doggy and it never shifts into high gear. Check engine light's on. Or maybe sometimes check engine light might not be on. Because not all transmission codes turn the check engine light on. You're going to want to see if there's faults in that transmission. If there is, it could have defaulted. So you could probably fix the problem, clear the codes, and it'll start shifting again. A default to a gear doesn't mean that the transmission is no good. I have seen it more often than not because technicians are terrified of an automatic transmission. One's in a default and it's got a code in it, like say a gear ratio code. They just automatically say, well, the transmission must not be any good. So they put a remanufactured transmission in it, and because that new transmission came with all new sensors, it shifts just fine and think, oh, I fixed it. When it might have been just something as simple as a solenoid or a speed sensor. Or they take a transmission that they have to change the speed sensor, take the speed sensors out of the old transmission. They put it on this new one, they put it in, and it's doing the same thing. Because the problem wasn't with the transmission, the problem was in the sensor. But if you get one that won't shift, it's stuck in one gear, most likely that means it's in default mode. It's seen a problem that could damage the transmission, so they lock it into one gear. So if we're going to summarize this lesson of what we learned, we're using electronic controls so we can more accurately take control of the shift points in our transmission, from how we shift under what loads and what speeds, how we control our torque converter solenoids, to even our adaptive shifts. In a non-electronic transmission, they didn't have any way to account for wear in the transmission. So as the transmission wore, then it would start slipping more and more and more, and then finally it'd burn up. That's why electronic transmissions have a tendency to last longer, because with these adaptives we can adjust pressure and timing to make up for that wear. So that if a clutch pack starts to get a little wear in it, we can increase the pressure so it doesn't slip as much when it's going into gear. So we can get more age out of our transmissions. And we're using sensors to monitor and our different inputs from our engines and our transmissions to control the the operation of that transmission. We're still using hydraulic pressure in our electronic transmission, but we're using our solenoids to control that fluid pressure, to move our shift valves. And then our PCM TCMs are using these inputs and outputs to control, using the inputs and our storage to control our outputs, all right, to control our speeds of our transmission. And if we have separate PCM and TCM, then the PCM and TCM has to communicate. So you could see where if we had communication errors between our PCM and TCM, we could have transmission problems to where once we fixed our communication problems, the shift problems would go away. So that kind of wraps up our lesson on electronic transmissions. Our next lesson will be in diagnosing transmissions, and this will be the whole process. This is our, if you remember from engine performance, our diagnostic process. There's steps to it. We have this very similar steps when we're diagnosing a transmission. We want to go through the steps as we narrow down our problem so we can repair that vehicle and get it back to the customer. And we're going to kind of cover both hydraulic and electronic diagnosis when we're in our next lesson. So just remember that the biggest thing I want you to get from this electronics class is to know that these transmissions, electronics transmissions, are still shifted hydraulically using hydraulic pressure. We're just using solenoids and sensors to control that pressure more accurately to shift our transmission.